I'll begin with a word of prayer. Dearly Father, we thank you for this day. I thank you again for the students. Thank you for the weekend that's about to start. You pray with us today. Help us again, Lord, to glorify you in what we do. In your name I pray, Lord Jesus. Amen. Okay, so today I will talk to you guys about determinants. Now, first of all, the question is, well, what is a determinant? Well, let me show you one way I can think of motivating what a determinant is. And it begins with a simple question. The question is this: given a square matrix with variable entries, let's say like A, B, C, D, E, F, G, so forth and so on. Just suppose you just label the entries by variables. What formula do you need for those variables in order to guarantee that that matrix is invertible? That's a question that we have not asked nor answered yet, except in the 2 by 2 case. In the 2 by 2 case, we already know that if you have A, B, C, D, a sufficient criteria for invertibility is that AD minus BC be non-zero, right? Remember the 2 by 2 inverse formula? What's the analog of that for a 3 by 3 matrix or a 4 by 4 matrix, or worse yet? Well, what I do here at the start of the chapter, which I have not posted for you guys yet, and that's as to not distract you. You should be studying everything except for this for the test next week, right? This is later. So the base case, of course, is a 1 by 1 matrix. You're trying to solve the equation AX equals to B. What do you need in order to invert for X? In order to multiply by the inverse is just 1 over A. Stupid, right? But in the case of a 1 by 1 matrix, we just need the matrix is non-zero. All right? Not especially exciting. The 2 by 2 case, we have this formula, right? So we need that AD minus BC is not equal to 0. That suffices. Now, in the 3 by 3 case, right, I know that A is invertible if and only if it reduces to what? Yes, to row reduced to the identity matrix, right? So what I do is I suffer through that calculation for arbitrary A, B, C, D, E, F, G, E, F, A, B, C, D, A, B, C, D, E, F, G, H, I, yeah. And I just to make my life not so unpleasant, I assume that the entries are all non-zero. If one of the entries was 0, you'd need a different derivation, right? Fine. It turns out that the outcome here would still be what you need, though. Yeah. Anyway, so I do the row. If you're trying to copy this down, you're doing it wrong. Okay? No, the point of this is I don't want you to copy that down, but you see it can be done. And after you do these row reductions, right, you'll end up with this. If you multiply that out, like so, you can factor out an A, and then you've got this, right? So in order for this thing to be non-zero, which is what I need, right? If this is non-zero, then I can rescale the last row to 1, right? So for that to be non-zero, I either need that this is non-zero or all that is non-zero. Okay? I've already assumed A is non-zero, so that's out. So it suffices then for this 1, 2, 3, 4, 5, 6 terms added together and subtracted, right? That being non-zero. And then that in fact, folks, is the determinant of the 3 by 3 matrix. So we could say this: a determinant is some formula that you come up with. It produces a number from a matrix, and if that number is non-zero, the matrix is invertible. Now, this does not uniquely define the determinant. Why? I mean, you see why that would be something worthwhile investigating, right? I mean, that's a simple thing to ask about. How do you find a criteria for invertibility? That's one of my. By the way, these formulas are not quite right yet. Just warning you. I mean, they're mostly right. That's not quite right, though. I mean, that's not enough, because if you have your equation, right, is a bunch of stuff not equal to 0, well, you can take a bunch of stuff not equal to 0 and multiply by 3, and it's still a bunch of stuff not equal to 0, and it's a different formula, right? So something else is needed to fix the formula for the determinant. And what it is that the determinant, and this is maybe even a better viewpoint of what a determinant is, the determinant is the volume. So, definition. the determinant, oh man, the determinant of a square matrix A is equal to the sum I1, I2, In. So this is a sum over n indices, I equals 1 to n, of epsilon, I1, I2, In. And then what I do is I have AI11, AI22, AINN. This epsilon symbol, epsilon 1, 2, 3, n is equal to 1, and all other values are obtained by the assumption of complete antisymmetry. What's complete antisymmetry? Complete antisymmetry is the notion that if I exchange any two of the indices in the epsilon symbol, I get a minus. All right. It's not at all obvious why this is the volume. But I promise you that this is actually the n volume in n-dimensional space of the n columns of the matrix A. Now, I should have told you A is what kind of matrix? Yeah, n by n is a square matrix over a field. Although I think a lot of what we're doing actually still makes sense over a ring. In other words, I don't actually need division in a lot of what I'm doing. Okay, let me just take a step back here. Let's look at this in the n equals 2 case, okay? N equals 2. So we have epsilon 1, 2. If I flip the order of epsilon 1, 2, I get minus epsilon 2, 1. All right? If it's completely antisymmetric, you guys have experienced this already in the study of antisymmetric matrices, right? Like epsilon 1, 1 is equal to minus epsilon 1, 1. Epsilon 1, 2, 2 is equal to minus epsilon 2, 2. So this gives us what? We have a complete story here. Epsilon 1, 2 is 1. Epsilon 2, 1 is equal to minus 1. And these guys are what? 0. So the construction of this epsilon, this completely antisymmetric symbol, is this idea that if any of the indices are repeated in it, 0. It's a way of destroying repeated things. And basically, it gives you a formula which is giving you a distinct set of n indices. The only way that the epsilon I1 through In is non-zero is if all of the numbers 1 through n are in that list. So in other words, the indices have to be distinct for the epsilon symbol to be non-zero. And it's either plus or minus 1. So epsilon basically, it's either 1, it's either minus 1, or it's 0. That's it. Just to complete the thought here, if I have the determinant of A11, A12, A21, A22, I get what? Epsilon 1, 2, right? See how they match? Okay, so 1, 1, A22, plus epsilon 2, 1, A12, oh, I'm sorry, the way around, my formula. A21, A12, which is what? This is actually equal to A11, A22, minus A21, A22. Sorry, 1, 2. you can recognize this is, if I change it to what? A, B, C, D, it's exactly, again, right, this is AD minus BC. See how it works in 2 by 2 case? Let me go ahead and let me just go ahead and unwrap the 3 by 3 case. 3 by 3 case. This is probably what I will view as a mistake when I go back and look at this lecture. See, my dream in this lecture is to finish determinants in a day, but I think my dream may be flawed. Okay, so this, right, is the sum over I, J, and K. I don't need I can just use, like I1 is I, I2 is J, I3 is K. I don't need the, the sub-index there. And so I have epsilon I, J, K, A, I1, A, J2, A, K3. In principle, how many terms are there here? 3 times 3 times 3. There are 27 possible terms. Yeah, E is right. However, only 6 of those are non-zero. Because if you study the epsilon symbol for 3, you get 1, 2, 3 is equal to 1. That's the starting point. And then epsilon, well, you work it out. 2, 2, 3, 1 is equal to epsilon 3, 1, 2. Those are 1. But epsilon 3, 2, 1 is equal to epsilon 2, 1, 3 is equal to epsilon 1, 3, 2. Those are minus 1. So you got 3 1s, you got 3 minus 1s. Just like the formula that I was projecting earlier that we found from row reduction, that sum of 6 things had 6 things, 3 pluses, 3 minuses, no accident, of course. This is just a slick way of writing those terms we found. And so what that gives you, of course, is like, well, let me just get to it. What it gets you is, how's it go? I'm trying to remember. Oh, fine. Epsilon 1, 2, 3, A1, 1, A2, 2, A3, 3, right? And so forth. This is kind of boring, isn't it? I should never ask that question. I won't like the answer you give me. Let's see here. Epsilon 2, 3, 1, A2, 1, A3, 2, A1, 3. Oh man, I'm sorry guys, I don't want to write that all down. It's there. So obviously for explicit computation, this is kind of a drag. This way of thinking of it, right? But it is a definition nonetheless that we have, which is super useful to know about for theoretical purposes, if nothing else. Now, there's another way you can fine, I want to actually write down the formula though, so let me try to do that. A11, A22, A33, minus A11, A23, A32, minus A12 times A21 times A33 plus A12 times A23 times A31 plus A13 A21 A32 minus A13 A22 A31. if I did this right, I should have 3 pluses and 3 minuses, and nothing should be repeated anywhere. Is that the case? All right, let me explain to you how I just did what I did. I didn't use the definition directly. I used what's called the cofactor expansion. So the cofactor expansion said there's a different way you can calculate determinants. What you can do is you look at, for example, I start with this A11, all right? And so what this really is like A11 times the determinant of A22, A23, A32, A33. See that? So this is A22 times A33 minus A23 times A32. That's these two terms. Then this one, it goes plus minus. I get minus A12 times the determinant of everything that's not in the first row and second column. So that's A21, A23, A31, A33. And you can check that these two terms, if you look at them, are exactly this, right? Because I have A21 times A33, right? That's this term. And then I've got minus A23 times A31, but that minus and that minus gives me a plus. That. And then the third thing in the top row is this one. So that's this and this, and what this is coming from is A13 times the determinant of A21, A22, A31, A32. Again, you can see, so what the cofactor expansion, this is called Laplace's expansion by cofactors or by minors. It's this idea you can take a determinant and you can break it down as a weighted sum of subdeterminants. So.
And this is just what the cross product is for vectors.
Ah, right. This is the same pattern as cross products. In fact, you can write a formula, right? By the way, good comment. A cross B from Calculus 3, for those of you who had it, you can write as the sum, ijk equals 1 to 3, of epsilon ijk ai bj x hat sub k. That's exactly the same pattern as this. And also, of course, you can do this, A cross B dotted with C, right? Well, that gives you this. It's a straightforward, if you take the dot product of this expression what I'm about to write, you get this formula, ijk equals 1 to 3, epsilon ijk ai bj. And think about what happens if you take the dot product of this with C. What you're going to do is you're going to pick up the ck component, right? Because x hat sub k, that's the unit vector in the k direction. That dotted with the c vector just gives you the kth component of c, all right? But this is nothing more than the determinant of A, B, C. And remember, we learned that this triple product is what? It's plus or minus the volume of the parallel pipette with edges A, B, C. If you've had Calculus 3, you should have learned that, right? If you look at something like this, and then, I don't know. I've almost made a convincing picture of a parallel pipette. I don't know. I was trying to draw A as the front edge here. Let me use some colors. My parallel pipette picture is pathetic. So here, A, that edge, B, this edge, and then C, I'll just draw it over here. All right? So like the magnitude of A cross B is AB sine theta. That's the area of the parallelogram. And then when you take the dot product with C, it picks off, it gives you the height, basically, and then you multiply the height by that area, and that gives you the volume of the parallel pipette. But this is only true, remember, it's the right-hand rule. Like A crossed into B goes which way? A crossed into B goes into the board. Don't worry, not part of this course. Relax. A cross B into the board. So my picture is valid. In fact, this really would give you the volume, you see? But if C was actually pointing the other direction, right? If my picture wasn't valid, if C was, if I just changed this C to be like this, if that's C, let's call it C prime. Well, C prime would be pointing out of the board, right? So A cross B is into the board. C prime's the opposite way. Actually, this would be a negative value. So the sign of the triple product tells you whether A, B, C form a right-handed triple. And so basically what that is giving a sense of orientation. These vectors, if you think about the set of vectors A, B, C, right? If the determinant of A, B, C, if that's greater than 0, what that means is if you think about the plane, like this is the plane, if that's the vector A and that's the vector B in this plane, all right? If the determinant of A, B, C is positive, what that means is that C is on the same side of the plane as the cross product of A and B. So like A cross B goes up. If that determinant is positive, that means that C is like somewhere up here. On the other hand, if this determinant is negative, that just means that C is below the plane. So determinants give you a way of deciding what's up and what's down, all right? Once you define one of the things as being up. But this is called an orientation, all right? So, all right, orientation is something, it's a property that's possessed by a set of vectors, not just one vector. And in case you need n vectors in an n-dimensional space to define an orientation. So more on that later, maybe not. I don't know. I forget what we talked about in here. Let's take it a day at a time. How about that? Anyway, so thank you for your question. I have digressed slightly, but these were digressions I wanted to make today, so it was useful. I think you can agree with me that it's volume, though, right? At least in the three-dimensional case, which you already are well aware of. And you could take this, or some of you are well aware of. Some of you have not had Calc 3, and that's okay. It's not okay, but I'll live with it. But this actually gives you a way of defining volume in higher dimensions where you don't have some kind of natural immediate geometric idea. This gives you a way of algebratizing, let's say, the notion of volume to n dimensions. If it works for 2 and it works for 3, how about the 1-by-1 case? What's the determinant of A? It's A. Sorry. And if it's positive, what's that mean? Going to the right? Yeah, whichever direction I've defined is you're right, there's the issue. Which way is right, which way is left? I guess it depends on, is it you guys or is it me, right? That's my right, that's your left. But anyway, yeah. So if the determinant's positive, A is going to the right, right? If the determinant's negative, well then A is on the left. So you see the sign of the determinant decides which way is which. That's true in 1 dimension, it's true in 20 dimensions. I digress. Questions? Let me work, yeah.
Just like jump to 40?
40? No. Okay, so yes and no. I need to define, I did a pattern for you, but I need to give you a more careful definition of that. So here's the definition. This is just an example of the cofactor expansion. I want to state it more systematically. So man, do I have a marker that works in here? So, let A be a square matrix again, okay? The minor, all right? The minor of Aij is, let's say, Mij, all right, which is defined to be the determinant of A with the ith column and jth row removed. So, like this right here. That's the minor. I also need to define the cofactor. The cofactor, very closely related, but there's a sign that's thrown in. The cofactor, the ijth cofactor, the ijth cofactor in particular, let's call it Cij, is defined to be minus 1 to the I plus j Mij. So there's a theorem. This is Laplace's expansion by minors. It's this determinant of A is equal to A I1 C I1 plus A I2 Ci2 plus dot 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 plus AIN CIN. And just same is true. You can do A1J C1J plus A2J C2J plus dot 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 plus ANJ CNJ. This is the so-called ith row expansion of the determinant. And this is the jth column expansion. Of the determinant. I was using that theorem when I shortcutted the calculation over here, right? Like, if I go back there, can you guys tell me, in terms of this notation, what is the thing in red, what's the thing in blue, what's the thing in green? No. The thing in red is C11. This is C12. This is C13, I think. Oh, I see what you're... Oh, I'm an idiot. What did you just tell me, Adam? That's A11, C1. Thank you. Yes, you're right.
So just the determinant in that is C1?
A12, C12. And this is A13, C13, right? Yeah. I'm sorry?
So C11 is the notation for the determinant of...
Right, C11, it's plus or minus, it's minus 1 to the I plus j times the determinant of the matrix with the ith column and jth row removed.
Okay.
And then you can do you just recurse all the way down. If it's 4 by 4, you get the sum of 4 3 by 3s, and then that gives you the sum of 4 times 3 2 by 2s. 4 times 3 times 2. Hey, 4 factorial calculations. So it's no accident there are 6 terms here. That's 3 factorial. The 4 by 4 is a sum of 24 terms. The 5 by 5 is a sum of 120 terms. The 6 by 6 is a sum of 720 terms. The 7 by 7 is a sum of 5,040 terms. And that's all I know for factorials. The point is, there's a lot of terms, right? So it'd be nice if we had some tricks to shortcut the calculation, right? This is one of the first tools, is this cofactor expansion. So here, let me show you an example. It'll be 4 by 4. So the determinant of 3, 0, 0, 0, 2, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 7. All right, I will do the, what do you guys want me to do? I'll tell you what, I'll do the column expansion. I'll stick with the first row, fine. I'll expand across the first row. So I get what? 3 times the determinant of what? And that's it, because you see the A12 and the A13 and the A14 expanding across the first row. Well, the others are 0, right? So the first row expansion just produces that. Are you with me so far? Does that make sense?
Yes.
And then you look at this, and we do the column expansion again. Tell you what, this time I'll be weird. I'm going to expand across this one. These are all zeros. So if I expand on that column, let's see here. Plus, minus, plus. It's plus again. So that's 1 times the determinant of everything not in the second row and second column, which is 2, 0, 0, 7. And then this is 2 by 2. I know the formula for that, right? 42. What do you know? If you watch lecture 26 of last year, I did a non-trivial 4 by 4 there, which also comes out to 42. But I think it's accidental. This one was on purpose. There's something, yes, sir?
I'm sorry, where is you have 3 times 1, and, I'm sorry, where did that 1 come from?
It's this one.
Okay.
Times the determinant of everything that's not, it's
Oh, okay, so you're looking at the corners.
exactly. So I'm this, and that gives me M22 as 2, 0, 0, 7. Not this, though. It's the determinant of that, right? That's the minor. Tell you what, let me do another example. Oh, but before I do that, I would be negligent not to mention to you that one of the theorems we have is that, well, if D is diagonal, say the diagonals are lambda 1, lambda 2, down to lambda n, then the determinant of D is just what? It's the product of the diagonals. So if the matrix is diagonal, you just multiply the diagonals. That's the determinant. We just saw that here, right? Unfortunately, if we had learned that before, we could have saved ourselves all this calculation. Oh well. How about this? The determinant of 0, 0, 0, 1, 1, 2, 2, 2, 2, 2, 3, 3, 0, 4, 5, 6, 6, 0, 6, 6, 7, 7, 0, 7, 7. Future test question. Well, maybe not. I'm not sure I have a test where I have determinants on a test. It may only appear on a take-home quiz. I forget. But maybe determinant would be something you'd like on the final. I don't know. We can talk about that later. It's not like you actually have a choice. I'm just pretending. But so here, clearly, one column stands out to me as the clear choice of where we should expand. This one. Because I have mostly zeros. So here's the deal. I go plus, minus, so I get minus 2. And then I have to do the determinant. By the way, everything else is 0. So this is the only one I have to worry about. I don't have to add anything else. So everything else, so what do I have? I've got basically just cross this out and just focus on everything else. 0, 0, 1, 1, 3, 3, 4, 5, 6, 6, 6, 6, 7, 7, 7, 7. Okay. And then you should probably focus on these ones, right? Expand on the top row. So that's equal to minus 2. The determinant, minus 2 times 1. Well, excuse me, plus, minus, plus. Okay, so plus 1. The determinant of everything that's not here and here, right? So that's 3, 3, 5, 6, 6, 6, 7, 7, 7. And then I need another color. Plus, minus, plus. So this is minus again. So there's the minus from the 2. So I have minus 2 times minus 1 times the determinant of everything that's not in this one and that one. So it's these guys. 3, 3, 4, 6, 6, 6, 7, 7, 7. All right. At this point, I think I've illustrated the idea of the expansion, both for a column and for a row. I'm going to stop there. I know now, and I'm going to tell you how I actually would calculate this. I mean, I wouldn't actually do it this way. This is a foolish way of doing it, because we also know properties of determinants. And we should use those to avoid this kind of calculation whenever we can. Let me just go through those with you. The determinant of A is I'm going to come back to that example in just a second. The determinant of A is the determinant of A transpose. Determinant doesn't care about transpose. That's kind of nice. Also, if there is even one row or one column which is 0, the whole determinant is 0. That's kind of immediately obvious from the formula for the determinant if you think about it, because it has, in everything that's added together, there's something that's coming from each distinct column of the matrix. So if any one of those columns is 0, and you could just as well write that in terms of rows, that is not at all obvious. This is a hurtful thing to prove. Whatever your formalism is, this is a hard thing to prove. It involves some kind of sneaky argument about permutations if you take that as your fundamental point. Mathematicians like to define determinants in terms of a sum over all permutations, but since I don't really want to talk to you guys about permutations this semester, I'm putting it off. Okay. Your book has a bunch of stuff about permutations. I really don't much care if you read the chapter on determinants in Curtis. Like I said, don't read any of this until after the test anyway. Even if you really want to break from abstract vector spaces and linear transformations, you should focus. I would sooner you check Facebook than to study determinants before the test. That's how strongly I feel about it. That's a very, very strong statement coming from me. All right. Sorry, Zuckerberg. That's just how I feel. All right. So if any column or any row is 0, the thing's 0. There's this wonderful property called multilinearity. Multilinearity means it's linear in each column. So like the j'th column, if I have a linear combination alpha Aj plus beta Bj, all right, the jth column is a linear combination of vectors, Aj and Bj, then you can pull out the alpha like that, and the Aj's there, and you can pull out the beta like that. That's the thing I was talking about, the incompleteness of my formulas, like that. So it is, if you fix everything else and you just focus on one, you get like a linear transformation from each column. But you have that n-fold times. It's called a multilinear map. That's a very precious and central property. In fact, you could define the determinant as the unique alternating multilinear map which sends the identity to 1. That's a definition people make for the determinant in other contexts. If you pull a scalar out of a determinant, you see you're pulling it out of every column. So it doesn't just pull out as k, it pulls out as k to the n. That's just almost immediately obvious from 3 if you think about it. If I multiply ka, what's that look like? It looks like ka1, ka2, right? Kan. So if I pull k out, I've pulled it out n times, that's k to the n. These are sometimes very useful. If you flip a column or a row, you get a minus. If you just add one column to another, if you do a row operation of this type, it doesn't change the determinant. Oh, and the one thing I forgot to say, maybe 7, if the columns are linearly dependent, or rows, then determinant of A is 0. And you can kind of see that from the multilinearity. If you have that, if you have linear dependence, that means you can write the one column as a linear combination of the others, right? So, well, anyway, it's true. And so, like here, this is very wasteful. Like, if I see this on a test personally, I'm just like 0 from the start. If you allow me this manga-style calculation, because these are linearly dependent. Done. 0. Aha. So, determinant apparently is yet another tool for detecting linear independence or linear dependence of a set of vectors, right? But without some further commentary, it's kind of not the most robust of tools because it only can check linear dependence or independence of n vectors in an n-dimensional space, right? I can check for n vectors, but I have to take a determinant of a square matrix. So if you ask me, like, I've got 3 vectors in a 5-dimensional space, are they linearly dependent or independent? Determinant wouldn't be much help there, would it? No, not directly at least. All right, there's still hope. Other important properties of the determinant. Other important properties of determinant, probably the most important property to determinant, and this is a big one, is that the determinant of a product is the product of the determinants. When I post the notes, you'll see that I give a proof in terms of elementary matrices. It's rather involved. This is not at all a trivial identity. It's not that easy to prove. Now, so I don't think I'm going to prove that for you guys this semester because I don't think the methods and the proof doesn't really lead to much anything else. It's kind of a dead end, theoretically, for us. So we're just going to assume that it's known. I mean, I do prove it in the notes. If you watched last year, you'll see I go through the proof last year. So there's another thing we know. Block diagonal matrices, what do those look like? So something like if you've got M1, M2, MK, something like this. So these are on the diagonal, right? 0 elsewhere. Well, it turns out if you calculate the determinant of something like this, it's actually the determinant of M1, the determinant of M2, all the way down the determinant of MK. Again, not a super easy thing to prove, and I don't think I'm going to prove this for you guys, but we will use it. Okay. You see an example of this, right? Like a super special case of this is that one. A diagonal matrix is a block diagonal where all the blocks are just 1 by 1s. Kind of silly, but true. All right. Check this out. If I'm trying to solve AX equals to B, and let's suppose A is invertible, right? I can do this. I can say, well, of course, A Ej is equal to the jth column of A. Let's say that A sub j is the, oh, excuse me. Sorry, column J of A. Right? So I could even do this. I could go, okay, well, look at this. So if I like E1, E2, dot, 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 X, En, and let's suppose that this is in the jth column. All right? You could look at that, right? Nothing stopping us. You say, why are you looking at that? I have my reasons. Relax. I have my reasons. They'll become clear enough. Multiply this by A. What happens? Concatenation proposition, right? Got yourself an AE1, AE2, da 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 da, AX, da da da, AEN. This is in the jth column. So what do we have? We have column 1 of A, right? Column 2 of A, all the way until we get to the jth column where we have what? B. Column N of A. All right? So, if you call this thing, let's give it a name. Let's call this whole thing A sub j. A sub j is, what that means is you take the matrix A, you leave everything alone, but the jth column you swap out for the inhomogeneous term, the B. Okay? And then on the other side, it's equal to A times this matrix. What's the determinant? So let me call this thing, I need to come up with a name for this. Well, fine, determinant of A times E1, da da da, E, X, da da da, En. All right, so the determinant of a product is what? Product of the determinant. So that's determinant of A times the determinant of, like 1, 0, da da da, 0, 0, 1, da da da, 0, and so forth until you get to X, and so forth until you get to the last column being 1, like so. And that's equal to the determinant of Aj, right? I just took the determinant of the equation above. What's this? Tell you what, let's just look at like a 3 by 3 case to understand what it is. The determinant of, for example, 1, 0, 0, x, y, z. Oh, I'm sorry, x1, x2. What is it? This one's easier. If you calculate this, right? What do I get? That's x2. This is x3 if you work it out. You can prove, in fact, that this is precisely x sub j. Therefore, x sub j is the determinant of aj divided by the determinant of a. This, my friends, is your beloved Cramer's rule. If I had another 10 minutes, I don't, but if I did, I could derive for you a formula for the inverse of a matrix, which would reproduce the 2 by 2 formula we already know, and give you a general formula for the inverse of a matrix. You're like, a formula for the inverse of a matrix? Why didn't you teach that to us? We did all these row reductions. The formula comes at a certain cost. It comes at the cost of calculating the determinant of n by n, n minus 1 by n minus 1 submatrices of your given matrix. So we're talking about like n factorial calculations for the inverse of an n by n matrix. That's a bad deal, because Gaussian elimination is something more like n squared. N squared versus n factorial, it doesn't take long for n squared to be the victor big time. The only case where this is kind of mediated is the 2 by 2 case, where we have this wonderful, simple 2 by 2 inverse formula. But that's it. Only a very, very silly person would memorize the formula for a 3 by 3 inverse. His name is Min. Anyway, with that, I'll stop.